Okay, good afternoon, everybody. Welcome. Everybody is doing well? It's been a pleasure to see people in person after, 18 months. Okay, so my name is Subhashish Mitra. I'm a professor at Stanford, and I'll be moderating this panel on hardware operation at scale, reliability to address silent data corruptions. We have distinguished panelists, Rama Govindraju from Google, Stephen Hensley from AMD, Sriram Shankar from, is it Meta or Facebook? What do we call? Okay, Meta, okay. I took some notes, I wrote Facebook. I feel pardon me for that. And Aryan Desai from Intel. Okay. So we are talking about silent data corruption. What the heck are the silent data corruption? Well, before we get into silent data corruption, first we are talking about reliable operation of computing systems. And hopefully, given that it's OCP, nobody will argue why we need reliable operation. So when we try to ensure reliable operation, a bunch of things might happen. Life would be annoying if we had a bunch of computer crashes or hangs or something like that, right? Still, life would be good, because unfortunately, there is a third kind, the most insidious type, the so-called silent data corruption, which means you perform a computation, everything looks great, but the results are incorrect, and you have no freaking idea that the results are incorrect. Mostly ignored by the systems community. So you go and talk to somebody in the distributed systems, they would say, well, we focus on what are called fail-stop failures. But today, silent data corruption is becoming a really big deal, as will be discussed in this panel. Now, what would cause silent data corruption? Software bugs, operator errors, errors in computer hardware, storage, you name it, it could cause silent data corruption. For a very long time, people used to think that compute hardware is just never vulnerable. It's solely reliable that you would never worry about computer hardware, especially for mainstream computing. But that has drastically changed. And here we are talking about compute chips. We are not talking about DRAM. These are the chips that perform computations, such as CPUs. And they have been identified as a major source of silent data corruption. Recent papers, some of you might be familiar. We have some of the authors in the audience and on the panel. From Meta, I didn't say Facebook, and Google, they have identified that silent data corruptions caused by compute hardware, like CPUs, can be very substantial at the scale of 1 in 1,000 CPUs or more, as we will hear from our panelists. And remember, this is not just a cloud issue. The cloud folks have massive resources to pinpoint the problem, unlike my mom, who would blame a compute problem to somebody up in Seattle, right? So we really need to thank our colleagues from Meta and from Google for all their efforts, and very importantly, for talking about it publicly. A lot of these could be hush-hush, nobody talks about it, nobody knows about it, but as a result, the whole compute community, and this is really, really important for OCP, would be totally blindsided about this significant and scary challenge. So let's give a round of applause to our colleagues at Meta and Google for really bringing this to everybody's attention. Now, you might be wondering, what would cause the hardware to produce silent data corruption, right? It could be logic design bugs. It could be soft errors from cosmic rays. But for today's discussion, the focus will be on manufacturing defects. These are defective chips that are not getting detected by manufacturing tests. And also, we will talk a little bit about what are called reliability failures, such as circuit aging. Now, for those of you that are the software types, FYI, chips are like human beings, and they age over time. And the chips that went through Stanford's tenure process, they would age much faster than the others, much significantly. Why are we talking about manufacturing defects and reliability failures? Because there is substantial evidence that this being the major cause of silent data corruption. So finally, the question is, how do we overcome this silent data corruption? And that's what this panel is all about. But let me share with you, since I'm the moderator, I get to speak. Uh, I actually, right now, at this point in time, don't see a single silver bullet. I couldn't tell you, do this, and the problem would be solved. So we must think holistically from new ways of hardware testing, or even monitoring during manufacturing, or maybe monitoring in the field, all the way to software-implemented hardware fault tolerance techniques and software techniques for system resilience. So the goal of this panel is to first acknowledge that this is a major challenge here, and we need to motivate all parties involved to overcome this challenge with the right incentives. And we need to move fast. Please remember, this is not a blame game going on over here, okay? So having said that, now what we will do is I will introduce my panelists. My first panelist is Sriram Shankar. He's the director of engineering at Meta, where he leads teams responsible for hardware health of the entire server fleet that powers large-scale devices, including Facebook, Instagram, and WhatsApp. Sriram previously led the engineering organization responsible for server and data center infrastructure at GoDaddy. Sriram, you want to say a few words?
Of course. Thank you, Subhashish. Hey, it's great to be here. Great to see people in person, but I also know people are looking at this online. So, it's this hybrid mode thing. So it's great to be at OCP again. With that, at Meta, we power services like Facebook, WhatsApp, Instagram, and the teams that I support work on. There are hardware engineers, software engineers, data center engineers, automation folks, data scientists. They work to make sure that the hardware that Meta has, it works as expected, right? What is as expected? And when we saw some of these things where you have a computation, 2 + 2 is 4, but then we see 5 or like 7 or like 500, we're like, computer doesn't work as expected, right? So, and Subhashish covered different things that I'm excited to talk about in the panel, but the core of it is computation, and what we expect of it doesn't work as expected, right? So, and that, earlier when we used to talk about it in the industry, it's not new, right? People used to say, this is 1 in a million problem, right? This happens, black swan event, it's very rare. But when we found that first issue, we debugged it. We took the application code, we figured out where it is happening, we're able to pinpoint it, but we didn't stop with that. We ran it across our entire fleet. Guess what? Then we can talk about now numbers and how frequently that happens. And then it is not 1 in a million, it is multiple orders of magnitude higher, closer to 1 in 1,000. When it is run of the mill, every 1,000 CPUs or every 1,000 devices, is going to have this issue. You need a different approach. You need a holistic approach. You cannot just think about it at the hardware level. You cannot just do silicon level stuff. You need to work at the application level. You need to do across holistically, like Subhashish mentioned. So, and after we did that, we've been partnering with our industry peers and our partners in the manufacturing side to make sure that we tackle it together. I'm excited to join the rest of my teams here, like Google, Intel, and AMD, and Stanford from a research perspective, who agreed to be on the panel, and look forward to this. Thank you, Subhash.
Thank you very much. Our next panelist is Rama Govindraju. Rama is the director of engineering at Google, where he leads the systems infrastructure performance engineering team. Previously, Rama was a distinguished engineer at IBM, where he was responsible for leading the software architecture at IBM's supercomputing lab, where he led the development of 5 generations of supercomputers. Rama?
Thank you, Subhashish, for the kind introduction. And I agree, this is a very important topic. And the first step to solving any grand challenge problem, which I believe this is to acknowledge that the problem exists and understand the scope of the problem. I think one of the key conclusions, which Subhashish said, there's no silver bullet. So what it really means is we need the entire community to be engaged in helping us address this challenge holistically, because there's third-party software, there's applications written by everybody, so it can't be an isolated approach to solving this problem. So the whole point of this panel is to raise awareness and make sure the community is alerted to the challenges that confront us and figure out how we holistically address this problem. Because finally, the trust of our users and the trust of the entire industry is at stake here. And I'm sort of saying this with the gravitas that it deserves, is that I deal with the software engineers at Google, and I can tell you they're very unhappy, right? Because we have lost their trust. And they are losing the trust of their users if these things start to become more and more visible. So we have to build mechanisms through the end-to-end stack. So improvements have to come from the CPU vendors, improved telemetry, improved reliability, improved testing, improved verification methods, improved software detection methods, improved system software, improved application software to be able to sort of check for these, build new methods, and build new approaches to addressing this challenge. If we collectively put our mind to it, I'm confident we'll be able to address it that in a manner that we'll all be proud of. But it's important to first acknowledge the challenge we face. It's important to acknowledge how difficult it is. It's important to engage the entire community, and hence this panel.
Great. Now, one thing I realized is that I failed as a moderator, because these Google and Meta guys are sitting on this side, and the hardware guys are sitting on this side. Can I ask one of you guys to swap?
Microphone people don't like
Oh,
it.
microphone people won't like it? Oh my gosh, okay.
I'm happy to swap, right? Just,
Okay, Intel and AMD want to go together. I seems like you really want to swap? Is that okay, guys?
Whatever you'd like to
If
do.
so I think let's mix up the hardware and the systems guys, right? Like
right.
kind of looks weird, right? Yeah. Yeah. I should have noticed that. So now I have to turn my head like this, okay? So Rama and Sriram, you guys have published on this, so thank you very much. But you guys have mostly talked about CPUs. So there is no problem with GPUs, TPUs, HTPUs, and it's only the people that
I can't comment on the GPUs. I will comment that even TPUs suffer from this challenge.
TPUs do suffer from this challenge.
Absolutely.
Okay.
And so it's not just a CPU vendor's problem. It is an industry-wide problem. And for a long time, the theory was that for machine learning, it doesn't matter because it's probabilistic and approximate computing anyway, right? Training, if it does not converge, training does not converge for any number of reasons, right? It could be some model's parameters are not right, training rate is not right, or your input parameters got mucked up, or any number of reasons can cause training to not converge. And if inference sometimes, a 6 is detected as a 0 or a lion is detected as a tiger, big deal is the thought. However, what you see is even in machine learning, it's starting to be applied in healthcare, in diabetic retinopathy, where accuracy is of critical importance. So no longer the case that you can assume that approximate computing or machine learning applications are immune to this. Not at all. This is a pervasive problem across the industry and will become more and more important as more applications start to leverage these capabilities.
Yeah. Terrific. You want to say a few words, Sriram?
I completely agree with Rama, right? I think our ability to use keywords and say, hey, oh yeah, AI will take care of it, that kind of approach is not going to work here because this is fundamental to how computation is done, how silicon is built, how we operate it at scale. So I feel like, similar to what Rama said, we need to look at it across the breadth where there is unprotected data paths, period, right?
Great. So now our next panelist is Stephen Hensley. He's the Vice President of Silicon Design Engineering at AMD, where he leads a cross-functional team whose mission is finding methods to detect failures during the entire product lifetime. Very important, a cornerstone to reliable compute. Steve is also responsible for key IP and architecture for the Infinity Fabric, AMD's central DFX team. For those of you that do not know what DFX is, it's called Design for Excellence. X is not for don't care, okay? Which includes design for test, reliability, and other features, and in general, reliability, availability, and serviceability architecture. Steve?
All right, thank you very much. Yeah, I noticed that we did swap spots, so we're not on one side, but we're the manufacturers.
Still
in the middle. We're in the middle.
Still you guys are tracking each other,
Yes, well, this is a very serious topic, right? I think it's been well explained, something that we need to take very seriously as we go forward. But one of the things, though, to bear in mind is we've seen these challenges before in the industry, right? So, you mentioned the radiation effects, and I think that's a good example to go back to. In the early 2000s, we did have this kind of thing, and it was silent data corruptions, some kind of thing. And we came together as a community, CELSI and various other things, and it took some time to figure out what we're going to do, but we did eventually solve that problem. We came up with a fault model. We came up with a way of thinking about this and how we can have a technique for our designers to use when we're designing for it. We came up with test methodologies, right, so that we could test this and standards with respect to that. So we do need to come together, but we also know we can solve these kind of problems.
Okay, that's great. So our next panelist is Aryan van de Ven. Sorry, Aryan. Aryan is an Intel fellow in the software organization, working mostly on open source software, and has been working with large cloud solution providers to help them manage systems with faults in their fleet. Aryan is a frequent speaker at open source conferences and often presents Intel Linux and open source strategy with senior management. Aryan?
Yeah. So I've heard a lot of glass half empty discussions already. I'm also a little bit glass half full as an engineer, meaning it's hard to solve, I'll give you that, but we can make these kind of things at least an order of two of magnitude better by just doing interesting software solutions in terms of screening fleets out, finding these issues, finding them quickly, getting them out of the fleets, maybe even make somewhat more robust software. So today I'm glass half full on this. I spent the last 2 years dealing with this with some of our big customers, and it's hard, but there's also a lot of things we can do. I don't want to give up before we start.
Fantastic. So what are the hardware folks doing about, are you guys making things available to the general public, on, like open sourcing stuff? This is open compute,
What we have done over the last several months is we have built a lot of tools in our manufacturing line and for our customers to screen their fleet, and we've made those tools available on our website for everybody to download and use. And we've started open sourcing chunks of that so that people can either look at the source code, help out, partner with universities, partner with our customers. Full disclosure, not everything is open. Some of our CPU-specific tests are still proprietary, but the tools are freely available for anyone to use and download. So we want, this is a serious problem, and part of the solution is finding the bad CPUs. The moment you know a CPU is bad, we know what to do. You take it out, you get the warranty, it's dealt with. Finding them is the hardest part.
So we really applaud you folks for doing that. This is I think is a very significant step. What about AMD? Now that Intel is open sourcing their tools, you guys?
Yes, we intend to also make some tools that we've been developing internally, right? Working with some of the select customers on that will be made available very soon. So in a similar kind of vein.
Okay, so so what's the objective over here? This is like SETI at home or proton folding at home, which is like everybody just you farm it out and people will find defective CPUs, or is it about like really kind of understanding like what these tools are generating so that
It's two things, right? Like you mentioned, sometimes there's an escape from the factory because we're improving our factories all the time, of course, but sometimes an escape from the factory, and we want people to find it in the supply chain or before the customers put it in production. But also over time, CPUs go bad. If a CPU is in production for 5 or 10 years, a certain percentage or sub-percentage will, it's over time just age.
Like the Stanford professors, right?
Yeah, they age out, and it's a bell curve. And if you have 1 million CPUs, that little early part of the bell curve hits you earlier than you think. So it isn't just a make the factory perfect. It is over the life cycle of the CPU, the people who operate the hardware, we need to figure out how to help them sort of find out when a CPU goes bad and take it out. So first of all, I think this is a very important step, and I'm very happy that at OpenCP, we are talking about this. But like wearing my academic hat, it sounds like if you just like make the tools to generate tests open source, but nobody had any idea about what those designs are that are getting tested, then you're not going to get much out of it. So are you planning on, I'm asking both Steve and Aryan, are you planning on making your designs available like on FPGAs or something like that so that people can actually go and do coverage metrics and things like that? I don't think we have plans to do that. We can partner with universities potentially, but one of the things I've learned over the last 2 years is that the traditional models for fault coverage don't work anymore. They have hit a wall, and new thinking is needed. And so far, the best results we've had is not by using the RTL design of the chip, but actually have very smart software people write creative software to find these issues. And it's been orders of magnitude more effective than going from an RTL model up.
So what do you think, Steve?
Yeah, so I think we need to back up just a minute.
Okay.
All right, so a little bit, we need to talk a little bit about some of the effects we see, right? So manufacturing defects is a very broad category, and what kind of things we're doing when we do tests, right? So things that get generally thought of as time zero defects, right? So coverage is a very complicated problem. That's what Aryan's referring to, right? We traditionally have had stuck at fault coverage, and the literature very much says, you got to start having transition fault coverage, right? And then if you expand on that, you get into cell-aware coverage, right? Where you go and you're looking at individual cells. And that's one of the areas that everybody's contributed. That's one of the areas AMD contributed, 10 years ago, like, hey, cell-aware is a thing we need to start paying attention to, right? And if you extend that further, you even look recently at ITC, I believe there was a paper where somebody said, look, it's not just cell-aware, you need to also look at multiple, transitions on those gates at the same time, right? And that, needs to expand the cell-aware sometimes. So the point being is, there's faults. We need to understand the fault models for these, right? And if we can understand the fault models, that's a good step towards solving this problem.
Right. So how are you going to understand fault models and their coverage metrics? I fully agree with Aryan, by the way, that the conventional models, like stuck at and transition, they're just plateauing out. They plateaued out many years back, and it's kind of surprising that the industry is still, stuck at, right? So how are you going to, make use of those new metrics, if I might call them, if somebody didn't have access to the design? So in my mind, I think Blackbox is not going to work. Now, maybe we can do a little fireworks over here right now, or we can move to the next question. So you think that Blackbox testing is the future?
So wait a minute.
Okay.
I don't defaulted to him, but if you don't mind.
Okay, go ahead.
All right.
Okay.
Right,
Yeah.
but if we can develop a fault model, right, we can, I'm sure the academic community has good ways of building.
Well, there are many fault models that are out there that the industry ignored for a very long time, yeah.
Right,
Yeah.
but do they represent the defect density
That's
we're
right.
seeing now of these very small
Yeah.
geometries,
Yeah.
right?
Yeah. Good. So you think that white box models are important, otherwise those fault models won't have much effects. And Aryan thinks that black box models are the most important things, basically. So the disagreement is good on a panel.
I'll explain why.
Okay, good. Okay.
This is from 2 years of experience dealing with this issue. So internally we have done both a white box and a black box. The downside of the white box model is that if you want to do it if you want to run these tests in an actual live system, the time that you take to run these models is many hours. You get great coverage, but it takes 24, 48, 72 hours to test the CPU. And if you want to do it every 3 weeks, that becomes prohibitive in terms of capacity loss. The black box models might not find the last 1% of the issues, but they do it in 20 minutes. And it becomes a very different, it's an effectiveness.
But that's a very well-known thing. Go ahead.
But the goal should be to get to every defect, right? So if
Thank you. Go
you're
ahead.
skipping something just because it's convenient, I think that would be a mistake, right? I think
I
I understand the challenge of the time it'll take, but that's where I think academic ingenuity can come in.
Exactly.
And sort of figure out smarter methods.
The hybrid, by the way, is an interesting one. That you create software tests from a black box model, but you evaluate them white box.
Right. And to do that, you need to give us access to your RTL.
Or at least a way to evaluate. You can imagine a cloud service where you upload your test and you get the result back.
Absolutely.
I can imagine the IP challenges of sharing RTL, but I'm confident that there are NDA models which can enable experts in the area.
There's a hybrid where you can say you don't get the RTL model, but you can upload a test, and a coverage metric comes back.
That could very well be true. That would be a fantastic way of doing things. I think we have to be innovative. I just wanted to start up the conversation, I just took an extreme position, for that.
I think there's ways to do this without saying everybody give your RTL
Yeah, of
out,
course.
right? So we've solved these problems in the past without doing that.
But you guys are agreeing that something has to happen
Something has to
beyond
happen
status quo, right?
beyond the status quo,
Yeah.
and there needs to be some research in these areas and development in order for us to move forward.
Fantastic.
One point I want to make, Subhashish, here is I think incentives work great. An example I'll take is the Netflix model, right? In I think 2006 or so, they had an open challenge saying, build a recommendation system that is 10% better than what we have today.
And
they
how
made
much
the
was the
data set
price tag for
anonymized.
that? Yeah.
I think it was a little over $1 million or something. They anonymized the data set and made it available. There were more than 80 entrants. Some very creative ideas came up. And now what we see is Recommendation systems are being used everywhere. YouTube uses it.
Yep.
Every system uses it. There are coursework on recommendation systems. There's separate courses, graduate level courses, advanced level courses, undergraduate courses. It's now become a routine practice to build a recommendation system within a quarter, right? So once incentives are right, very creative ideas form. So I think the key is for the industry to create those incentive structures for the smart folks to sort of apply their creative minds to these hard problems.
Absolutely. And
So one more thing on that, OCP as the Committee on Hardware Fault Management, and maybe it's all open compute, open systems. So call for action to the community here could be like, hey, let's make it open.
And OCP could play a very important role in how this would be managed, for example. So, oftentimes people tend to say that, oh, this is the problem of the hyperscalers, like Google and Facebook, and my mom is never going to see this problem, right? So what's your take, Sriram and Rama, on that,
Yeah, I can go with like our story here of like finding the first problem, right? I mean, if your mom found it too, if it's a problem that matters to her, it is an important problem. We are in this business to make sure our customers are happy, and one problem versus a million problem shouldn't distract us from the goal of keeping computation accurate, right? So that's the high level. But then you have a point, like with higher scale, like with better statistical kind of like time and like run, we are able to find things better. But it's definitely not an hyperscaler only problem, right? It's even the magnitude that we shared in our paper shows that even if you have a smaller installations, if you're running on cloud, you're more likely to run into this than what the industry ever thought before, right? So that's my pitch. Rama, please.
Yeah, I totally agree with Sriram. I mean, it's not a hyperscaler only problem. Even those with modest installations probably are experiencing this. What may be different for hyperscalers is the ability to correlate these as being able to sort of verify that this is due to SDC, right? Very few centers have the engineering manpower to be able to dig through some of these challenges. These are just needle in the haystack kind of problem that you have to go about determining and confirming that this is a bad CPU or bad chip here. So many centers probably face this. They probably just dismiss it as a software bug or some overflow bug or what have you and restart the system and hope it goes away. But they probably don't convert what they are seeing to be isolated and verified as a bad chip. Whereas now with hyperscalers, with our engineering teams, and at hyperscale, you cannot do anything manually because you won't be able to scale. So you have to build automation. So with that kind of an engineering effort, you can get better statistical information as to what you are seeing, how to correlate events, and sort of be able to build signals to see where else you might be seeing this problem and finding those more faster. So we might have an advantage in terms of the ability to find these much more easily than maybe, not so easily, but it's still comparatively easier than other installations. But I don't believe this is a hyperscaler problem only at all. It's clearly far more widely prevalent.
You guys, the hardware guys,
I agree.
Yeah.
That's also the reason why we made our tools widely available, not just to the hyperscalers.
That's fantastic.
So on that,
yeah.
I would even go far to say it's a tip of the iceberg problem here. It is not, hyperscalers are finding it according to Rama, but how much are we not finding? Right?
Yeah, I'm sure we're not finding a lot. So that's what scares me even more.
That's right.
You're absolutely right.
That's right. We don't know how deep the iceberg is, right?
Yeah.
So that brings the question, Rama, you made a very interesting point, and we did not dwell on it, which was like you said, we should find every defective chip, right?
Yes.
You said that. So Sriram, you want to find every defective chip, or you're happy with like some kind of a
Absolutely. The question to ask, I want to find every defective chip.
So Aryan, you were talking about, like being efficient, right? Hey, like we all know when you do random testing, like in the beginning you catch a lot of stuff and then you hit that plateau, right? Yeah. So what are you hardware guys going to do about this? Like they want to find every defective chip. Steve and Aryan.
So we're making our factories better, right? That's for the time zero defects. That's all we can do. For the things that happen during the lifetime, we're trying to make more and more advanced tools that you can run on your system to catch these things.
Is this really true that, go ahead, Rama.
No, finish your thought, Brad.
Yeah, is this really true that even for the time zero defects, that's the only thing you can do is to make your factories better? Couldn't you do something else? couldn't you provide, infrastructure so that, you could apply, like a lot more patterns? Maybe days of testing, in the field.
That's what.
Right? That's not time. That's still time t equals to 0 defects, right?
Absolutely. And if that's what we do with our supply chain. Some of it happens in our factory, but think of it as before put in production, everything until that point is almost a supply chain. So it can happen anywhere in the supply chain. That's okay.
Okay. Yeah.
I just want to elaborate on why I emphasize that we have to find every defect. One thing to note is these kind of defects, the cost of recovering from those grows exponentially over time. So if, let's say, Aryan and Stephen are able to find it in their factories, it's practically no cost to us.
1x,
Maybe some delay in shipping, right? Once they ship it to us before we deploy it into our data centers, if in our QA we catch it, there's some cost. It's more than what it would have been earlier.
Right.
But once you put it into production, sometimes the corruption incidents can be amplified such that the cost just escalates.
10x,
It's very, very
10x
hard
level,
to
right?
recover lost data when you detect it late. If it's a fail stop, we have already mechanisms by which we can reconstruct data that was sort of corrupted or what have you, and rerun the logs or what have you. But when it goes silent and you detect it very late, the effort taken that it needs to reconstruct what might have been lost and sort of get things back to stable, because these are all distributed systems. A corruption here can sort of go somewhere else. A key could get corrupted, sort of making large swaths of data unavailable, right? Security keys could be corrupted. So these things multiply as you delay your ability to find these defects, then the costs just escalate. So that's why it's very, very important that every defect is caught as early as possible, right? So these guys have to do better. Our QA has to do better. Everyone has to be able to do better through the chain here.
We'll come back to the cost question, but Steve, your perspectives, and let me sneak in another question, both Aryan and Steve. I was talking to somebody, from IBM, and they said, oh, this problem has been solved. The IBM Z Series machines have solved all these problems. And that's a way, maybe you should just buy IBM Z Series machines for your cloud. So, or maybe you should upgrade your architectures with the IBM Z features.
Yeah.
So, Steve and Aryan, go ahead.
Yeah, well, that's an interesting comment. I happened to, you alerted us that maybe you'd ask that question, right? And I happened to talk to a few people from IBM, and interesting, I don't think they all said they solved that problem, by the way, but they did have an interesting take on this, right? And if you look at some of the what they put out, I think they had the mindset of, what do they call it? Bulletproof compute, right? No data loss, no downtime. And then if you go look at it, they had a whole checkpoint architecture. They had a replay unit, all this. You can actually
Logic parity checking.
Yeah, and you could see all these things. You can even see it on the die. There's a large part of the die with respect to that. And I think what it's kind of back to what I had said a little bit earlier, right? There are potentially techniques out there that we should learn from each other and from other places. And there's probably new techniques to get out there and do there. But it's a continuum. It's a continuum of where we are in the power, performance, area, the cost the market can take, right? And the reliability, right? And we got to find the balance that's there. But on top of that, we also need to be able to understand, how do we measure those choices, right? So we don't want any defectivities. We were aligned on that. But at the same time, how do we measure where we stand, right? And so that's part of what we need to come together as a community to do.
Yeah,
Great.
I think
Sriram, go ahead.
Right,
Yeah.
there is an important distinction here, right? We want to find the hardware faults as soon as possible, as early as possible. The goal is not designing zero-fault hardware, right? I mean, there are trade-offs in cost on the other side of designing zero-fault hardware that we are not necessarily kind of pushing. We are saying, hey, we want to find it as soon as possible. We want ability to detect it so that doesn't impact our customers.
Yeah.
That distinction.
That's a very good point.
Yeah.
0.0 is really hard because even no matter what architecture you do, if you have 3 or 4 bad transistors that cancel each other out, even your most advanced replay logic will just once in a million go wrong. It might be very unlikely, but 0 is a hard number.
Right.
Yeah, it's a hard number, but that's the kind of aspirational goal we should have. But I think coming back to the cost question that Steve raised, which is a very valid concern, but I don't think we should dismiss the cost equations of various options very easily, because There are smart ways to sort of do this, like the Z Series IBM's reliable systems. They have lockstep execution capability. I know it's sort of a tremendous cost to add. However, we are smart enough now to be able to design it such that it can be selectively enabled or disabled. So maybe Stephen and Aryan give us chips that are enabled with this lockstep, and in the first 3 months in production, we run it with lockstep. Right?
And then
if we find that these things are not are running smoothly, great, then we can disable it. So the extra cost of this lockstep execution is only incurred in the first quarter.
And it's amortized
of its life, and it's amortized over 4 to 5 years.
Well,
okay, go ahead.
So I was just going to say, I mean, I understand the concept. I think the idea, though, is interesting. The idea that there's some mode of operation that maybe you kind of, on a new technology especially, right? You do something, you can get some learning on that's a more reliable mode of operation, right? And then after you've done the learning there, you can move forward without that, right? Or maybe it's application dependent. Maybe there are certain applications where, okay, I got to go into that mode, and you don't know others. So, I don't think we want to get caught up on the solution, but the concept I think is great.
Yeah, but I was using this as an example to say that cost, sometimes there are creative ways to adapt and amortize, right?
Yeah.
And also that will give us some data points on, let's say in the first 3 months, all the bad chips were detected in the first 2 weeks. Then we know we can actually shorten the 3 months.
Yep.
But let's say we are continuing to find these bad chips close to the 3 months. We know we need to run actually longer in this mode, right? It'll give us data points to understand the scope of the problem.
And that's a good example of what I would call cross-layer, right? Yeah. You have some hooks in the architecture, and then you use your systems, infrastructure to enable them, in creative ways, so that the overall cost goes down, right?
But the software person in me says, but the hardware can do lockstep. Why can't the software? Because hardware lockstep is more than 2x in terms of performance, right? It's probably more like 3x. So, what can you do this in software at a higher level? So that you only have a 2x cost instead of a.
But that has its trade-offs, like then somebody has to compile the software with software implemented hardware fault tolerance, for example, right?
No, but I think the thing is to have both, right? I mean, it's not one versus the other. I mean, right now in our fleet, we run opportunistic testing across our entire fleet, software driven, right? But we find a lot, and my question more is even when we have all of these methods, we may still miss a lot of these issues.
What is the effectiveness? Nobody knows the answer, right?
Exactly, right? Yeah. How do we motivate the industry to come to that? How to make it a culture of figuring this out? I think I'm more interested in that. So of course we all need to do our part. Hardware mechanism needs to be there, software mechanism.
I've been asking too many questions, but maybe we should let. Yeah, you wanted to say
I just want to add to Aryan's point. I mean, sure, software can and should also do it. In fact, we first detected that this is a problem because big tables, 2 of the tablet server checksums matched, the third one did not, right? And the third one always did not match when executing on a particular server, right? So, but the problem is that you want your systems to be used by everybody. Not everyone has the engineering resources to build fault-tolerant software, right? So both have to be done.
Absolutely.
I think Sriram is absolutely right.
I agree.
Yeah.
But there's a trade-off to be made. Sometimes the software is more effective at doing it, and sometimes it's the hardware.
And the software can be selective. Okay, these are critical paths. These are areas that I need to be extra careful and sort of do this, right? But it also sort of, the other point I made about finding defects as quickly as possible to reduce cost requires that hardware also do its part. So it can't be one or the other.
I agree.
Right.
And even it's not just about what you detect. You also have to understand what the heck is going wrong, so that you don't repeat that thing in the future, right? So that you learn, and maybe you have new fault models and you create tests so that next time they're screened. So, I've been talking too much, right? So do you folks, the panelists, have questions for each other that, you want to ask?
I have a question for you.
Ooh, okay.
I would be interested in knowing, you as a researcher, what would be your wish list from...
This is not set up, by the way, okay? Although it did warn me that I should be prepared with that. Okay.
What would be your wish list from the hyperscalers as well as the CPU vendors to really make your research work more productive and help, get the creative minds onto it?
You did warn me, Rama, and I actually thought about it. And then what I decided is that I would take the high ground and talk about, more higher level aspects of this, and then we can delve into details, of, what the nitty-gritties are, what the tactical things are, right? But in general, I think, I was literally thinking about this. I spent time on it yesterday because Rama warned me. I think what is really important, what we are talking about is business as usual is not going to fly anymore, right? So, he was talking about fault models plateauing out, right? Rama talked about, innovative ways of doing things. Steve talked about, hey, maybe, they're going to put new stuff in the architecture. Sriram talked about, hey, opportunistic testing, how the heck can I do this? But, I think it's fair to say, and I don't want to offend anybody, none of us on this podium are going to do it, right? It has to be done by new generations of students. So I think the first most important thing is that you must inspire academics. Especially I actually have written this down because I want to say this right, okay? You must inspire academics, especially the software and systems folks, to work on this problem. You must explain to them what its importance and the profound impact it can have. Believe me, most software and systems people believe that hardware reliability is not a problem. And to get there, and this is where I'm urging Meta and Google, that you must publish at highly visible forums, that raise public concerns about this. Archive is good, HotOS is good, but they are not enough, okay? You cannot just sneak it in there, saying that, we have a publication at Archive and HotOS. You have to be at very visible venues, okay? So that's my first point, okay? Saying that, look, we got a problem, just like Spectre and Meltdown got a lot of press, basically, you have to do that. That's my first thing. Feel free to jump in, while I'm talking, okay? The second one is, in this field, it's very easy to get caught up into, here this bunch of defective things, basically, and, why don't we have a bunch of hacks or some uneconomic, brute force approaches to detect a bunch of defective chips? I think we cannot afford to inspire that kind of research. We really have to inspire research that's based on quantitative principles. That's why I brought up this whole point, right? It's fantastic that, the tools are available now, in open source. And there might be ways of, like NDAs and things like that, so that new test metrics, and new coverage metrics can be calculated based on the RTL and whatnot, right? I think we need quantifiable principles with solid technical foundations, not some slippery slope. I ran this thing and I found that it was catching a bunch of defects. And I do not think, that's going to fly. That would be my second point. The third point is, as I said, that, access to tests or even defective hardware. Now, are you guys going to make defective hardware available as well? I'm just looking at companies,
It's hard to do it to a general public, but to a specific university where we just have a partnership, absolutely.
Okay, but if some university comes to you,
absolutely,
you would go and do that. That's actually a really good first step, and I'm assuming AMD would say yes too,
well,
because Intel said so.
I mean, the thing I think we should think about, right, is we need to do things that will help move things forward, and defective hardware generally. That will tell you a certain class of problems. But I think our experience is that what we're dealing with is a much broader set of things. So if we get too focused on a specific number of parts.
Correct. We need principles.
We need more of the principles than, hey, these specific parts we found.
Right. So that was my actually third point. I don't know how many of you, this is kind of a systems forum. Some of you might know about Professor McCluskey at Stanford University, right? He was the pioneer who actually transformed testing from kind of black magic into a scientific field. And he did this, what are called the Murphy and Elf experiments. This was in the 1990s. And that actually set up things from where all this cell aware and all that stuff comes from, basically. Yep. I really think that the industry-wide, we need a thinking of that kind of a massive experiment to really understand where these defects are coming from. How could every defect be detected? Not somehow, I just found a bunch of stuff, basically. That would be my, fourth task. And then the fifth task is, earlier I talked about inspiring academics, right? You just, put it on, New York Times or someplace. But you have to really motivate academics. And one of the ways to motivate academics is what?
Funding.
Significant funding, And I mean significant funding. You cannot just throw $500,000 at somebody and say, that's it. And this is where perhaps there is an opportunity industry-wide for you to work with the government even, like the US government is, the CHIPS Act and all that kind of stuff. I think these are my few asks. Like inspire academics, go and tell the software people that this is a really important problem to work on. Publish, at major venues, not, HotOS and archive. Quantifiable principles, McCluskey's kind of experiments that he did in the 1990s, and significant funding.
Sounds good.
So, more questions for each other? We have like around 5 minutes left.
Audience question also.
Oh, audience has a question. Great, fantastic. Can you identify yourself?
I work for Meta, and I worked for Intel for the last 20 years.
Okay.
And I have been working in the fault handling for many, many years at Intel. And my question is really, see, this problem, it's not a rocket science. This problem is not unsolvable. Fundamentally, if you can detect a fault, if you have a logic to detect a fault, then at least you have detected it. If you don't even have a logic, then it's going to be silent. So it's a very simple concept, right? So why we don't work on improving our detection logic within the silicon? And I actually worked in the past several years working with the architects to even push, hey, these are the areas you can add the detection logic. And there has been a lot of pushback in the past. So my question really to both AMD and Intel, what are you guys doing to improve the fault detection logic within the chip? Why are we not adding that to cover the most common faults that results into silent errors?
Not most common faults, all faults, right? Okay.
Well, at least start with the most common and then get to,
all. We'll march to all.
I mean, we are right now in a point where this is like a, I would say, I don't want to say cheating, but at least what CPU vendors have been telling, our silent SDE DPM is just like maybe 100 or few hundred DPMs. But the reality is much higher. So why are we hiding this? Why are we not being very upfront, saying, hey, this is what the real thing is, okay? And now let's solve it by adding more detection logic. Forget about correcting, just detection.
Okay, so good. I don't think we're hiding it. I think we're here on stage talking about it. So that's sort of we're publishing tools, we're publishing open source projects. I don't think anybody here that's on this stage is hiding things. So that's the conspiracy theory. I don't think is a valid one. I can also say that with the experience of the last few years, in partnership with our customers, we are adding as much logic detection as we can. I'm not a hardware designer, but I understand that in some places that is sort of relatively obvious, well known how to do it, and there's a lot of places where it's not. If you add two numbers, you can do a parity check at the end, and you can do that. But what do you do with a square root? So academics have figured out sort of self-checking algorithms for a whole bunch of basic things, but not for the more interesting things that are more areas. And adding a small multiply is big, square root is bigger in area, and these faults are sort of proportional to area, just by the nature of defects. I have yet to see anybody saying, hey, the actual interesting parts of the logic, we know how to do these self-checks. For the boring parts, yes, and yeah, you can assume that everybody's starting to do that in their chips. But for the interesting parts, I've not seen it yet.
Steve?
Yeah, I think, we didn't spend much time out earlier, but these are, oh, sorry, Rami, did you have
No, go ahead, finish your thought, then I have a thought.
All right, these are difficult problems, right? I think there was a paper from Intel at ITC that talked about how complex these problems are, right? Went through the marginal defects, right? And talked about how, these aren't, you traditionally would think, you test and you have a very nice curve, very good pass-fail region. They went through types of defects where you can have speckles or certain types. They're very complex, and that's a very interesting, illustration of that. That's not a single technique that's going to get that. And discussions of, hey, a circuit might have been designed with appropriate margin or a path with appropriate margin, but the defect hit that, right? And then hit that. And it's not just that that defect hit that, right? It often, in order to find that defect, it's not finding it under normal test conditions. It's finding it under a situation where, there's some workload that's had some level of coupling, some kind of DIDT because there's something going on in the package, to pull the supply down. It's a very complex problem to solve. So, it's more, I agree in concept that we need to do our right effort to put in the right fault detect logic. But some of these problems, we still need to figure out how we're going to solve them and how we do the right thing to get
I think the real question is, what's the best way to do it? Like, is it like testing it out? Or is it like, in the hardware architecture or in the software? And I think time will tell, and that's why, I think the academics need a lot of funding to do that. Yeah, please.
Yeah, I totally agree.
They're closing down, but
yeah. I totally agree with your question because it very importantly solves two problems that Subhashish wanted addressed. Right? First is he wanted the academicians to be inspired. Nothing inspires them than the data that shows the scope of the problem, right? If there's real scope, here is the real challenge that you're facing. That will be the most inspirational. But it also addresses the last challenge that he pointed out, which is funding. Once the government agencies know that their rockets and what have you are susceptible to these kind of failures, or their NSA's, whatever, mission-critical systems are susceptible to this, you will see funding pour in more than Subhashish can handle, right? So I think your question is very, very valid, and the whole purpose of this session, I think, is to shed light on this problem.
To start this
Sriram's words I'm borrowing is, the whole purpose is let's shed light on this problem so that more and more people get engaged in sort of addressing it.
Yeah. Okay, so yeah, go ahead.
It's a great segue on what can OCP do, right? I mean, we are in a panel, we are in this like kind of largest global symposium. I know, Anil, I mean, like a bunch of folks in the audience are involved with a bunch of committees. I would like to also we made an open call for access, more open sharing of tools. What that is, I feel like we have an opportunity to inspire not just academia but also the industry to contribute into this open forum. So I want to push in for the panelists. If you have other thoughts, or for the audience, do reach out to any of us or OCP subcommittee on fault management.
I would say no single one company can solve this.
Absolutely.
We need to do all of it, be in this together.
Yes.
Great. Hey, let's thank our panelists.